In section 2.6, we are learning about logarithmic differentiation as well as the derivative rules of transcendental functions that we haven't learned about yet. And so we're going to review some properties of logarithms from Algebra 2. And I want you to note that they are similar to some properties of powers that we know. So the first is that if I have a log of a product, so the log of the product, a times b, and these examples are with the natural base, but this could be any base log. If I have a log of a product, that becomes a sum of the logs. So the natural log of a plus the natural log of b. And I want you to think how this is kind of similar to a property of powers that we learn. That let's say that I have, x to the power of a times x to the power of b. If I multiply two powers with the same base, I know that I would add their exponents. So in working with powers, we already associate this condensing multiplication to addition. And so this is kind of the opposite, that we are uncondensing multiplication of a log to addition of two logs. All right, similarly, the log of a quotient. So if I have the natural log of a divided by b, that becomes the natural log of a minus b. And note that the order in which we subtract matters. So if I think about my powers rule, if I have some power, let's say x to the power of a divided by x to the power of b, I would subtract my exponents. So again, this is a similar rule, but it's almost the opposite rule because we are, in this case, condensing our power when we subtract, where we are expanding our log when we go from a quotient to a difference of logs. All right, and then finally, if we have the log of a power, so in this case, the natural log of a to the power of b, I could pull the exponent of the argument out and think of that as a constant multiplier. And I might again associate this idea of powers with multiplication when I think about my properties of powers. If I have x to the power of a, all of that to the power of b, that becomes x to the power of a times b. So for us to go through the proof of why these three properties exist, that would make this video much longer. I'm not going to do it in this video, but if you're interested, I'd be happy to do that in a different video. All right, so we are going to learn this process called logarithmic differentiation that allows us to use these properties of logarithms to make our derivative easier or just possible. So the time that we'll use this most often is when we are taking the derivative of an expression or a relation that has a variable in the exponent. So this will allow us to do this by this process called logarithmic differentiation. And it's just a few steps. We are going to take the log of both sides. We're going to use some combination of those properties above to algebraically rewrite what we're working with. Then we will take the derivative. So in this first example, we're taking the derivative of x to the power of x. So notice that this is not an exponential, nor is this a power rule, because this is x where the base is a variable to the power of x, where our exponent's also a variable. So the first thing I'm going to do is I'm going to call this y. All right, now we're going to take the natural log of both sides of this equation. All right, so using our properties from above, we now have on the right-hand side the log of a power. So I can rewrite this as x times the natural log of x, where my exponent, that was my exponent x, pops out and is a multiplier out front. So now this is in a form where we could take the derivative of this, of the left and right side of our equation. This is implicit differentiation on the left-hand side because we're taking the derivative with respect to x of something that's going to have a y in it. So when I take the derivative of ln of y with respect to x, I get 1 over y times y prime, or dy dx. So again, that's just from the chain rule. On the right-hand side, I have to use the product rule. So the derivative of x is 1, so I get 1 times ln of x, plus x times the derivative of ln of x, which is x times 1 over x. All right, so on the left-hand side, we still have 1 over y times y prime. On the right-hand side, I might just rewrite this as the natural log of x plus 1. Now our goal is to isolate y prime. Well, we could multiply both sides of our equation by y in order to do that. because on the left-hand side, y times 1 over y just becomes 1. So we now have y prime equals the natural log of x plus 1 times y, but we don't want to have a y in our final answer. So if I go back up to what I started with, we said y is x to the power of x. So our derivative here is the natural log of x plus 1 times x to the power of x. And I'm not going to distribute that. I'm just going to leave x to the power of x as a factor in my derivative. All right, let's look at the second example. So we are given y equals the sine of x to the power of the natural log of x, and we're asked to take the derivative. So the first thing that I'm going to do is I'm going to take the natural log of both sides. So the natural log of y will be the left-hand side of my equation. The natural log of the sine of x to the power of ln of x is the right-hand side. And so now, using my log properties on the right, I know that if my argument to my logarithm has an exponent, I can pop that out front. So ln of x becomes a multiplier. This becomes ln of x times ln of sine of x. So the natural log of x times the natural log of sine of x. And now we got rid of our variable expression that was an exponent. So now we can take our derivative. So again, on the left-hand side, I'm taking the derivative with respect to x, so I get 1 over y times dy dx or y prime. On the right-hand side, I do have to use the product rule. So 1 over x times the natural log of the sine of x plus 1 over the sine of x. I need to multiply by the cosine of x as part of the chain rule times my first factor, the natural log of x. So when I go to clean this up, I still have 1 over y on the left. I might think of this as ln of sine of x over x plus, well, this becomes, this becomes cosine of x divided by sine of x. I'm going to rewrite that as cotangent of x times the natural log of x. And then finally, we can go ahead and multiply both sides by y because we don't want our derivative to have 1 over y in it. When I do that, I'm multiplying the entire right-hand side of the equation by y. So on the left-hand side, I have y prime. Again, I'm going to rewrite this, the natural log of the sine of x over x plus cotangent x times the natural log of x. And then again, instead of saying times y, I really want to go back and replace y with the sine of x to the power of ln of x. So if you're ever working a multiple choice derivative question and you see, and it looks kind of crazy like this, you've got a variable expression in your exponent, you might notice that your answer choices are all going to have your original function y as part of the answer choice, as a factor of your answer. And that is sometimes a clue to us that we have used logarithmic differentiation here. So I'm not going to distribute sine of x to the power of ln of x, but rather leave it as a factor. Another time we use logarithmic differentiation is to make finding a derivative easier. So algebraically, the algebra steps in the beginning might be a little more to think about, but it's going to make it easier. So imagine if we did not, imagine if we just tried to take this derivative. We have the cube root of x squared times sine of x divided by e to the x times the quantity 2x minus 5 to the 9th power. I would have to use the quotient rule. I would have to use the product rule in both parts of the quotient rule, and I'd have to use the chain rule when I get to the part about 2x minus 5 to the 9th power. So using logarithmic differentiation, we can use our log properties to rewrite y. So I'm going to take the natural log of both sides of this equation, so the natural log of y on the right. And when I'm taking this natural log, I'm also going to rewrite the cube root of x squared as x to the 2/3 power. So x to the 2/3 power times the sine of x over e to the x times 2x minus 5 to the 9th power. Okay, and so we can apply several of our rules up here. So if I look, I have a log of a quotient, and within my quotient, my numerator and denominator are both products. So we could break this down. You might be comfortable breaking this down in one step. I might do a couple of steps here. So I'm going to start with the quotient. The outer structure of what I'm logging is a quotient. So this becomes the natural log of x to the 2/3 power times the sine of x minus the natural log of e to the x times the difference to x minus 5 to the 9th power. All right, so now we have a difference of logs, but we also, each of those logs has a product in its argument. So I'm going to apply the rule that lets me turn a log of a product into a sum of logs. So this is going to become ln of x to the 2/3 power plus ln of the sine of x. I have to be careful here with my subtraction that I put my next two terms in parentheses, or sometimes I switch to brackets. So then I have the natural log of e to the x plus the natural log of 2x minus 5, all of that to the 9th power. All right, so lastly, I'm going to rewrite this one more time, and notice that of the things we just wrote, 3 of those terms have an exponent. So we could use that property one more time to simplify this up a little bit. So this becomes the natural log of y equals, I could think of this as 2/3 times the natural log of x plus the natural log of the sine of x. I'm going to distribute this subtraction as I go through, or distribute the negative rather. So minus, I'm going to pull my exponent x out. So this becomes x times the natural log of e, which is just 1. Or I could just think of the natural log of e to the x is just 1. And then finally, plus 9 times the natural log of 2x minus 5. All right, so now we haven't taken the derivative yet. All we have done is rewrite our function y using the properties of logarithms. So now it's time to take the derivative of both sides. So on the left-hand side, again, we get 1 over y times y prime. On the right-hand side, 2/3 times the derivative of the natural log of x. Well, 2/3 is just a constant multiple, so I get 2/3 times 1 over x. For my next term, I'm going to get 1 over the junk, so 1 over the sine of x times the derivative of the junk, which is cosine of x. For my next term, we said that really x times the natural log of e is just x times 1. So the derivative of negative x is just negative 1. And then finally, for my last term, I have the constant multiple of 9 times 1 over the junk, so 2x minus 5, times the derivative of the junk from the chain rule. I'm going to pick up a times 2 there. All right, so I still have my 1 over y times y prime. I'm just going to clean this up a little. That is like saying 2 over 3x. Again, we have cosine of x divided by sine of x. That's just the cotangent of x. I have minus 1. And then in my last term, I could multiply that 2 and that 9 and think of that as 18 over 2x minus 5. So finally, I really don't want that 1 over y. I'm going to multiply both sides by y. And we get that y prime is 2 over 3x plus the cotangent of x minus 1 plus 18 over 2x minus 5. And then all of that junk times our original y. So I'm going to go back and substitute the cube root of x squared times the sine of x. All of that junk divided by e to the x times 2x minus 5 to the 9th power. All right. As you can see, that's a lot of fun with logs, but that is a much easier way to take the derivative. All right, on page 26, we want to learn a few more rules, and we can prove these rules to ourselves using logarithmic differentiation. So for example, up until now, we have learned how to take the derivative of e to the x. You know, that's just e to the x. And we've learned to take the derivative of log base e of x, so the natural log of x, which is just 1 over x. But we have not learned yet a general derivative rule for an exponential with a different base. And we've also not learned the derivative rule for a logarithm with a different base. So like, what if I want to take the derivative of a log base 10, for example? Well, we could either use the change of base formula to make it base e, or we could learn another rule for logarithms, or for derivatives rather. All right, well, let's look at this. We can use logarithmic differentiation to prove all of these things. So if I start with my first example, 2 to the power of x, again, I see that I have a variable as my exponent, so I could use logarithmic differentiation, write that y equals 2 to the power of x, and then log both sides. So when I do that, again, the whole point of using logarithmic differentiation is to use this property to simple this up. So I'm going to pop my exponent x out in front, and this becomes x times the natural log of 2. So now when I take my derivative, I know the left-hand side is 1 over y times y prime. I want to be careful here. This is just a constant multiple, right? X times the natural log of 2. Think about if I just had 5x there. If I took the derivative of 5x, I would just get the coefficient 5. So when I take the derivative of x times the natural log of 2, I just get the coefficient natural log of 2. So finally, we want to multiply by y on both sides. And we said our y is 2 to the power of x. So when I finally take my derivative here, I find that the derivative of 2 to the power of x is 2 to the power of x times the natural log of 2. And I bet you could probably think it through and infer some other derivative rules. Like if I took the derivative of 5 to the power of x, I would get 5 to the power of x times the natural log of 5. So if you go back and you think about our rule with e, if I take the derivative of e to the power of x, I get e to the power of x times the natural log of e. Well, that works because the natural log of e is just 1. All right, in the next example, we have y equals 3 to the power of the tangent of x. So again, I could probably think about what I just did with base 2 and think of that as just a chain rule problem. But again, we could go ahead and prove this to ourselves like using logarithmic differentiation. So if I take the log of both sides, so the natural log of y equals the natural log of 3 to the power of the tangent of x, and again, on that right-hand side, I'm going to use my properties of logarithms to rewrite this as the tangent of x times the natural log of 3. So now when we take our derivative, on the left, again, 1 over y prime, that's just an implicit derivative. And on the right-hand side, well, remember, the natural log of 3, again, is just a constant multiplier. The natural log of 3 is a value. So the natural log of 3 kind of comes along for the ride. The derivative of the tangent of x is secant squared x. And then I know I want to multiply both sides by y to clear that 1 over y on the left. So we get that y prime equals the natural log of 3 times secant squared x times 3 to the power of tangent of x. And so I might even, it doesn't really matter what order we write that in. So if I think about it, it's my original function, 3 to the junk, times the natural log of 3. And then from the chain rule, we pick up secant squared x. So similarly, I could just think about what we did to 2 to the power of x, but using a base 3. So 3 to the power of our junk times the natural log of 3. And since the tangent of x wasn't just x, the chain rule gives us secant squared x. So there's a couple of ways we could think about that one. All right, for these last two examples, we're looking at a log with a different base. And again, we only know how to take the derivative of the log with the natural base. So we could either use the change of base formula that we learned in Algebra 2 to rewrite this as log base e, and that would be fine. Or we could use logarithmic differentiation again to prove this. So let's go ahead and call this y. So y equals log base 2 of x. Now, I don't think logging a log will be particularly helpful here, but what I could do is I could undo the log function by exponentiating both sides with a base of 2. So in other words, I'm using the inverse function And on the right-hand side, when I do 2 to the power of log base 2 of x, because these are inverses, we just get x. So now we have 2 to the power of y equals x. So now we have our situation where we have a variable in our exponent. So it would be helpful to take the natural log of both sides. And again, using our log properties, I could think of this as y times ln of 2 equals ln of x. So now we're ready to take the derivative. We've just been having fun with algebra rules. We haven't even taken a derivative yet. So on the left-hand side, the derivative of some number times y is just that number, right, ln of 2, but because it's times y and we're taking the derivative with respect to x, we're going to get a y prime there. And then over here, our derivative of the natural log of x is just 1 over x. So for me to isolate y prime, all I have to do is divide both sides by the natural log of 2. All right, so our derivative here, y prime, is 1 over x times the natural log of 2. And notice that 2 is the base of our original expression here. So again, you might be thinking about how we could generalize this. Well, it turns out, let's say that I took the derivative of like log base 4 of x. Well, I'm probably going to get 1 over x times the natural log of 4. So let's think, if I took the derivative of log base e of x, and yes, that is the natural log, I would get 1 over x times the natural log of e in my denominator. And again, the natural log of e is just 1. So when we say the derivative of the natural log of x is 1 over x, we're kind of simplifying this rule that it's 1 over x times, in the denominator, the natural log of the base, but it's base e, so the natural log of e is 1. In this last example, we can, again, use the chain rule and what we just generalized about taking the derivative of a log of any base, or we could also prove our derivative using logarithmic differentiation. So again, if y is equal to log base 4 of 3x squared, we could go ahead and exponentiate both sides of our equation using the inverse. So we get 4 to the power of y is equal to 3x squared. So now when we take the natural log of both sides, the natural log of 4 to the power of y on the left, and the natural log of 3x squared on the right, we can really use our log properties to rewrite both sides of this equation. So the natural log of 4 to the power of y becomes y times ln of 4. On the right-hand side, we could actually just leave this as it is. It's not that hard to take the derivative of the natural log of 3x squared. Or I could think of this as the natural log of 3 plus the natural log of x squared. And actually, if I want to go one step further, instead of writing that x squared, I write that 2 times ln of x. So popping that exponent 2 out in front. Okay, so now when we take our derivative on both sides, we get, again, we just get ln of 4 times y prime, because ln of 4, you could think of that like the coefficient of y. We pick up a y prime, that being implicit differentiation. On this side, the natural log of 3, since that's a constant, that derivative is going to become 0. And then when I take the derivative of 2 times the natural log of x, I just get 2 over x. So when I simplify this, I get 2 over x divided by the natural log of 4, so that's like times the natural log of 4 in my denominator. So again, all of these properties of derivatives for exponential and log functions, we can generalize all of those with what's in our box below. So again, just generally speaking, anytime I take the derivative with respect to x of an exponential function of any base, so a could be any base, we could prove our derivative rules using logarithmic differentiation. So if I take the natural log of both sides, I use my log properties to rewrite the right-hand side, so that becomes x times ln of a. When we take the derivative in this step of both sides of our equation, on the left-hand side, we get 1 over y times y prime. So again, that's just implicit differentiation there. On the right-hand side, we just get the natural log of a, because again, that's like our multiplier or our coefficient of x. So when we multiply both sides by y, we get a to the power of x times the natural log of a. So for any base, if I'm taking the derivative of an exponential of any base, not necessarily our natural base e, I'm always going to get a to the power of x times ln of a. All right, and then the same goes with our rules for taking the derivative of the log of any base. So if I take the derivative of the log of any base a of x, again, we're going to think of rewriting this as y equals log base a of x. We can exponentiate both sides. So that means I'm going to rewrite this as a to the power of y equals a to the power of log base a of x. And again, we do that because log base a and our exponential base a are inverses, so they undo each other. Then when we take the natural log of both sides, we could rewrite that as y times the natural log of a equals the natural log of x. And so when we finally get to the step where we're actually taking the derivative, that was all just a lot of rewriting our equation and manipulating it. We would get the natural log of a, because it's just the derivative of y times ln of a. So the natural log of a times our y prime equals 1 over x. And then we would multiply both sides, divide both sides by ln of a. So y prime equals 1 over x times ln of a. So our general rule, and we probably just want to memorize this rule, is that the derivative of a log of any base of x is 1 over x times the natural log of that base. And when I say times, I mean it's in my denominator. So 1 over x times 1 over ln of a.